Welcome back to our weekly dynamical systems seminar. Our today's speaker is Alexandre from Purdue University. He'll tell us about anti-holomorphic dynamical systems on a torus and with application.
Thank you for the invitation. So since this is a dynamical semester, I already gave 5 talks without any dynamics, so let me give a dynamical talk. So from the point of view of dynamics, I'm going to show you a holomorphic dynamical system parameterized by C, where hyperbolicity is density in the parameter space. Okay, proven? Huh? Yes, proven. Proven. I will prove it today. So what is P from my point of view? Well, of course, this is a complex plane, but for me, this is a modular space of lattices factored by singularity. So let me introduce lattice. So this is a set of the coin and omega 1 plus n. Another C where I normalize omega 2 over omega 1. So this is called tau, and imaginary part of tau is positive. And then we have invariants of the lattice. So they are traditionally called G2, which is 60 times sum of omega minus 4, and G3, which is 140 sum omega minus 6. Okay, so these are homogeneous. Prime means that 0 is excluded, and so these are homogeneous. Now, up to similarity, the space of lattices is one-dimensional, one complex dimensional. So they are distinguished by the so-called J invariant. It's a homogeneous expression. And this is it. Okay, it exactly parameterizes the similarity classes of lattices, and the point of introducing all these quantities is to make it invariant with respect to the choice of generators. So this tau is not completely invariant with respect to the choice of generators. You choose different generators, you obtain different tau, but this is an absolute invariant. So it is exactly parameterizes like this.
Then you had omega 1, omega 2, and suddenly you go without index, right?
Yeah, here it's all omegas. Okay.
Okay.
So sometimes I use 1 and 2, sometimes for simplicity. Okay, so now there is a Weierstrass P function for lattice defined like this. And its integral, which is called the Weierstrass zeta-function. Defined by such normalization and the derivative of this zeta function is which is P. Okay, so P is periodic with respect to the lattice. It's a monomorphic function in the plane. Zeta prime is not, zeta is not exactly periodic. Okay, and accordingly we have periods of this zeta. Okay, and well, and now P satisfies the differential equation. With these G2 and G3 as coefficients. And if you factor this, it is written as P minus E1, P minus E2, E minus E. Okay, so these are all notations that we need. Okay. Okay, so now I come to the subject of my talk. So the subject of my talk is solving this equation. Okay, where A and B are unique constants which make the left-hand side periodic with respect to the lattice. Their explicit expression can be written, but you don't have to memorize it. It's a simple exercise to obtain this A and B from the condition that this is periodic with respect to omega 1 and omega 2. Well, for completeness, I will write the expressions, but they will never be really used. What is important for us is that this is real, and A is not necessarily real. No.
Do you have explicit formula for the etas?
Okay.
For the etas, eta 1 and
Eta 1 and eta 2 are defined here.
But can you write them as a functions of the omega?
Yes. Everything can be written as a function. So these are so-called modular forms. So there are multiple, all these things. So there are multiple expressions for them. And of course, everything can be written in terms of omega. These are functions associated to a lattice. Okay. Okay, so I can write this equation as a fixed point equation. Let me call this G of V. So this is a fixed point of an anti-holomorphic function, which is defined by the right-hand side. Okay, B is real. And this is my dynamical system. So the parameter space is P, which is the moduli space of lattices. This is T. Okay. Motivation. So why did we consider this equation? So the first motivation, it has a simple interpretation. It's a green function of a torus.
alpha A
Torus.
in the dynamics equation there is an alpha, but I think it's a big A. No?
Where do you see alpha? That's A. Ah, sorry. Okay, thank you. Green function of a torus. So what is a green function of a torus? Torus is compact, so there is no green function in the usual sense. So this is a best substitute. So this is the solution of Laplace G equals minus delta function plus constant. So this is the, okay, the torus here is the factor C over the lattice, and this is the area, Euclidean area. Okay, so that is by definition this is called the green function of the green function of a torus. So the question is, how many critical points does it have? Okay, and it is easy to understand why the gradient of the green function is the left-hand side of this equation. I will explain it. So green function has a logarithmic singularity at one point, and then constant Laplacian on the rest of the torus. So if you take a gradient, logarithmic singularity becomes a first-order pole. Okay, and this is the function which has a first-order pole. The origin of the torus. Now, what is the function with constant Laplacian? Quadratic in x and y. So its derivative must be linear in x and y. Here it is, this is the linear function in x and y. And the whole thing must be periodic, and this determines the constant thing.
This delta is delta. What is
It's a delta function, yeah. It's a delta function at 0. Lots of one z is 2, 1 delta. Okay. Is this clear? Okay. Where is it? Oh. Okay, so this is a gradient. This is a gradient of green function. Okay, and we are interested in how many critical points in green function. Well, I will explain why it has at least 3. So here is the torus. Okay, so these are the values of my green function. So it has a pole at some point, and you see, think of green function as a height in this picture. Okay, 1. So by topology, it must have at least three critical points. Okay, so the answer is 3 or 5, depending on the modulus. And it's amazing that this answer was not obtained in 19th century, but it was obtained in 2010 by Zhang Shaolin and Wang, who was his teacher. In a paper in Acta Mathematica, which is almost 100 pages. And the second paper tells you in terms of J, or how, when it is 3 and when it is 5. And this is another 100-page paper. So it is in the attempt to make sense of these complicated arguments, which involves nonlinear PDE and things like that, that we considered this equation by the means of complex variables, and it turns out that dynamics gives a simple answer to the question. Okay, this is a joint work with simple proof. Is due to Weierstrass and myself. Okay. Now, what was the motivation for this? So the motivation for this was explained in my public lecture. Which was called Matrix of Constant Positive Curvature on compact Riemann surfaces, but the compact Riemann surface in this case is the torus with one conic singularity with angle 6. So I will not describe the state of affairs. So the general question is, when does there exist on a compact Riemann surface a metric with constant curvature and conic singularities? Well, conic singularities is clear what it is. You take a sector and you identify sector with Euclidean or spherical or hyperbolic metric, and you identify these things isometrically, but alpha can be as large as you wish, it can be more than 2. Okay, so this is a conic singularity, and the question is when such a metric exists, which describes singularities and construct angles, and when it doesn't. So for curvature negative, constant negative, a complete answer is known. The necessary and sufficient condition is Gauss-Bonnet theorem, and the metric when exists is unique. For Euclidean case, it is even simpler. Again, the necessary and sufficient condition is Gauss-Bonnet theorem, and the metric is unique up to scale. And for spherical case, it is wide open, and this is why we consider the case of torus with one singularities. So what is known in general about torus with one singularity?
Excuse me, when you go there depending on torus, this if you could clarify the sentence depending on the torus.
For some tau, it's 3, for other tau, it's 5.
Okay, so this torus is not the one that you are now talking about.
No, I announced arbitrary torus for any tau.
Okay.
I described all tori. Okay, so for some tori, the Green function has 3 critical points. For other tori, it has 5. And the question is how to tell which is the type of torus, how many critical points it does have.
I guess my question is because all of them are topological tori, so in which they have.
No, but they have.
It's the holomorphic.
But they have. But Green function depends on holomorphic structures.
I see.
That's the question.
This was my
Yeah.
question.
All of them are topological tori, of course. But you cannot define a green function on a topological tori. Okay, so what is known for tori with one singularity? So let's consider a set of all metrics. I will call it SPH 1, 1. So 1 is a genus and 1 is one singularity of alpha. So this is the space of all Riemannian metrics. On tori with one singularity with angle 2 pi alpha. Okay, so then we have the forgetful map. So to each metric, to each Riemannian, for all Riemannian metrics of curvature 1.
You explained it already once, and you remind me metrics here, you understand.
All Riemannian
After multiplied by the star function.
of curvature 1. Okay, on tori was one singularity and then two pi.
But your Riemannian metrics are related to the holomorphic structure.
And this is what I'm going to say.
Okay.
So now you have the what we call the forgetful map. Which assigns to each Riemannian metric the corresponding conformal structure. To the moduli space 1, 1. Okay?
I simply have to ask, why is it called forgetful map?
Huh?
Why is it called forgetful?
Because it forgets Riemannian metric and leaves on the information about conformal structure.
No, but he gave the previous talk.
Riemannian metric is a way to measure distances and angles. Conformal structure only angles. So you forget distance.
The relation was that start with conformal structure. These metrics are just multiplications.
There are many.
Functions.
If you start with a conformal structure, there are infinitely many metrics conformal with respect to this structure. And if you start with a metric and assign conformal structure is an equivalence class of metrics. Equivalence relation is proportional.
Field of ellipses.
Yeah. So you put to each Riemannian metric conformal structure. I mean, Riemannian metric measures distances and angles. Conformal structure only angles. Okay. So this is why it's forgetful map. So this is moduli space of tori with one point, with one marked point, and this is what I introduced in the very beginning. This is a CJ. Okay. Now, what is the situation? So, if we are asking whether on a given conformal torus such a metric exists and how many, so we are asking about how many pre-images has a point under forgetful map, and also we are interested whether forgetful map is surjective. Okay, so for tori with one singularity, the situation is such.
But you want constant curvature.
Yeah, curvature is one.
Curvature is one.
All the time. Okay. So, so these are the metrics of curvature one only. I only consider. Okay. So for tori, the situation is the following. So if alpha is not an odd integer, this map has a topological degree. I will explain what is this. And this degree is M. where 2m is the closest integer to alpha. The closest even integer to alpha. So this means that in particular the map is surjective. Now what is the topological degree? So if you have a smooth map, which I draw as a vertical projection, then you take a point in the image, generic point in the image, you count the images, and you not just count, but you count them with a sign of Jacobian. Okay? And add. And the result is called, it doesn't depend on the generic point here, and it is called the degree. So in particular, topological degree, Brouwer degree, also Rere-Schauder degree, okay? So if it is not zero, then the map is surjective. Okay, if it is defined and is not zero, then the map is surjective. So, so the situation is the following. So here is 2m, and here is 2m plus 1. This is alpha axis. Okay, so on the interval around 2m, degree exists and is constant and equal to m. So the forgetful map is surjective. So for each torus, you have at least m such maps with such angles. Okay, but then it jumps at each odd integer. Okay, it jumps by 1. And for odd integer itself, the degree is not defined. It is not a map of, it's not a proper map. The degree is not defined. So the first interesting unsolved case is when m equals 3. Sorry, when alpha equals 3, the first case, which corresponds to the angle 6 pi. And we are interested in what happens in this case. Okay. Now, it is easy to understand where our equation comes. Where does this equation come from? So you pull back the metric to the universal coupler, to the plane. Now, each metric of, so this is the universal cover of my torus. So each metric of constant curvature 1 is locally isometric to the piece of round sphere of C with spherical metric. So you have this isomorphism, local isomorphism F, but since it is an isometry, then it is analytic, so it has an analytic continuation everywhere except the singularity. But since the singularity has angle divisible by 2 pi, there is no monodromy about singularity. So this extends to a meromorphic function in C. Well, a monodromy must be a commutative group of rotation of the sphere, and the commutative group of rotation of the sphere, there are two. Two types. One type is a subgroup of a circle, and another type is so-called Klein-Form group, which is D2 times D2, which does not occur here. Okay? So the monodromy is isomorphic to a subgroup of the circle. So this gives us the equation Okay, rotation in the circle. So this is what this is called the developing map. Well, it's not a map since it is multi-valued on torus, but if you pull it back on the universal cover, it becomes single-valued and satisfies this equation. So this is one requirement. And it must be meromorphic in C. And the second requirement is that it has only one singularity. So F prime has a single zero of order 2, which corresponds to the triangle per period. Okay. So one has to, one is interested, this is a complete characterization. One is interested in how many such functions are there. And so these beta J are real. So such functions can be written as follows. So you do the usual trick. You take log and differentiate. So the f prime over f will be already periodic in the usual sense. Now it has single zero of order 2 per lattice. So an elliptic function, the number of zeros is equal to number of poles. So it has 2 poles. And by Abel's theorem, these poles must be symmetric. Okay, and of course the residues must be of opposite sign, so that the sum is 0. And finally, it must be 0 at 0. So you add beta of A. Okay. So then, so this is the general form of any such function, where A is unknown. Okay, and now integrating this. You obtain that f equals e to z zeta of A sigma, or I have to say what is sigma of z minus A over sigma of z plus A. So sigma is a Weierstrass sigma function, which is defined by, it's an entire function. And it has one simple zero per period. Okay, so sigma prime over sigma is zeta. Okay, so now you write, you use the periodicity relation for sigma. It is the following: 2 eta z plus omega times sigma of z. And now I want to write the condition that these multipliers have absolute value 1, and using this and this explicit form, this gives me my equation for A. So this gives beta of A A plus B A equals 0. So this is the motivation for it. Okay. Okay, so now if you don't have questions for motivation part, I will start proving the result. Okay. So each metric corresponds to a solution of this equation modulo. So solution Z gives the same metric as solution minus. Okay. So now we are in the realm of anti-holomorphic dynamics. So I'm going to iterate this function. It's anti-holomorphic function in C. Of course, I cannot do this because it has poles. So this belongs to a well-investigated subject of dynamics of meromorphic functions. It's a meromorphic function. So as a map from C to C, it is not defined at the poles. Now, iterates will not be defined at the images of poles. So you take, so the P is a set of poles. M is the set of poles of M's iterate. And you consider what is called Purdue set. It is C minus order of those BNs. Okay, so this is the maximal open set where the iterates are defined. And the last is called any questions? The rest is called the Julius set. This is how Purdue and Julius set are defined for meromorphic functions. Purdue set is completely invariant. And okay, so the left-hand side is periodic. This means that G of Z plus omega equals G of Z plus omega. Okay, this is equivalent to the periodicity of that. So this means that the whole dynamics goes down to the torus. Okay, so can be considered as a map of some part of torus to itself. So okay, so we have a projection map from C to the torus, the universal cover map. And everything on the torus will be denoted with tilde. So F tilde is a map, and it is well defined on Purdue sets with tilde. And so on. Okay, so here is a plane. So here we have Purdue set. as a projection. Here's a torus. On the torus, we also have the two sets. So this is the picture. Okay. Okay. So now I'm going to employ the main theorem of holomorphic dynamics. So this is called Purdue theorem. So let D, so suppose that you have a map D to D, holomorphic. And suppose that it has an attracting fixed point. Then this map is not a covering. Well, as I stated, it is actually not even a Purdue theorem, but it is a Schwarz lemma. Okay, so each the D is assumed to be hyperbolic. So a hyperbolic domain has a hyperbolic map. Every analytic map between hyperbolic Riemann surfaces is compressing this hyperbolic metric. This is what Schwarz lemma really says. And it is a covering if and only if it is a local isometry. Should I explain anything about this? Okay. So if you have an attracting fixed point, you cannot be a covering. So now what does it mean that there is not a covering? This, well, in rational dynamics, this means that F is a critical point. But we are not in rational dynamics. Our map is transcendental. Okay?
Your map is it's not holomorphic.
Well, it's forget it temporarily. It's secondary that it is anti-holomorphic because I can take a second iterate and it will become a holomorphic. But the main thing is that it is not algebraic. It is transcendental. So what does it mean not a covering? This means that it either has a critical point or an asymptotic curve. And what is an asymptotic curve? It's a continuous curve gamma, 0, 1 to D, such that gamma escapes from D. Where infinity is a one-point compactification, the added point of one-point compactification. But f of gamma has a limit, which belongs to D. So this is the definition of asymptotic curve. Okay, so if you have a and the curve which tends to the boundary, but don't have to tend to the boundary like this. It may tend like this. Okay, but the point is that the curve escapes from D, while f of z on this curve tends to a limit which is in D. This is called asymptotic. Okay. Well, nevertheless, our function, our concrete specific function, doesn't have asymptotic. So, you have no asymptotic. Okay, so this is a tedious verification of definitions. I mean, I'm not going to go into details. Roughly speaking, if it has an asymptotic curve, then this pulls back to an asymptotic curve of G. Why did I? Sorry, why I call it F? It is G all the time. It's a G. I started with G. Okay. So it has no asymptotic curve, because if it were an asymptotic curve, it will pull back to an asymptotic curve in C. Now, if this asymptotic curve ends at a finite point, then having an asymptotic value in D will contradict the complete invariance of the Julia set. And if this asymptotic curve goes to infinity, then you can easily see that this function cannot have an asymptotic curve going to infinity, because this zeta is bounded away from small neighborhoods of the lattice points. And this part, of course, tends to infinity, so G tends to infinity away from some small circles around poles. So there cannot be any asymptotic curve. There cannot be a finite limit on any curve going to infinity. That's okay. Okay, so this is about the asymptotic curves. Now, each attracting domain must each basin of attraction must have critical. But what are the critical points? Sorry, it's not homomorphic. Okay, so I have to be more careful. So you consider the second iterate, which is holomorphic. Okay, then each attracting cycle must contain an orbit of a critical point. Okay, so look at the orbits of critical points. So what are the critical? So zeta prime equals minus 8. Yeah, so this means prime 8. And since P is an elliptic function of degree 2, this has two solutions on torus. Right. So we have two critical points. Moreover, P is even, sorry, P equals. So P is even. So these two solutions are of the form C and minus C. Okay, so we can have at most two attracting fixed points. Well, but our task is to count all fixed points, not just attracting. So to estimate the number of all fixed points, we look at the Jacobian of G. So in general, Jacobian of F, I suppose symbol F is not occupied yet. It's F with respect to Z minus F with respect to Z bar. Right? This is a general formula for Jacobian of a smooth map. Okay? But for our map, so what map? We consider the map phi. Okay, so this is a map. So I recall that this is periodic. Yeah, it's our left-hand side of our equation. So this is a map from torus. Okay. So what is the Jacobian of this map? It's 1 minus absolute G prime squared. Well, where G prime is, of course, D bar G. D bar is in this D bar. Okay. So we see the following. That, and of course, Jacobian is responsible for preserving or reversing orientation, defining the Jacobian. Okay, so we conclude that at attracting points, orientation is preserved, and at repellent points, the orientation is reversed. Okay. Next step is to apply degree formula to this phi. So this phi is an honest map between compact surfaces, so it has a degree. Okay, so what is the easiest way to carve the degree? Find the preimage of some point. Well, the simplest point is infinity, and the preimage of infinity consists of one point, namely the origin, where G has a pole, and since G is anti-holomorphic, the degree is -1. Okay. So this means that the number of zeros of phi which are also critical points of G, where orientation is preserved, and number of zeros where orientation is reversed satisfied n plus minus n minus equals -1 by definition of degree. Okay. Therefore, and we proved that those where orientation is preserved are attractive. And there are at most 2. Okay? So we know that n plus is at most 2, and n minus equals n plus 1. So the total number of solutions n plus and n minus is at most 5.
Is it somehow obvious that there are no neutral fixed points?
No,
Okay, thank you.
not obvious. But suppose that there are none.
Okay, then.
Okay? So suppose that at all points, Jacobian is non-zero. So this proved the theorem in this generic case. Now, to prove it in general is easy. Modulo 1 general theorem. So we consider the map instead of G, we consider the map G plus W. Okay? Since the derivative does not depend on W, all arguments can be repeated literally, and it gives the estimate that it has at most 5. At most 5. Fixed points. Okay? But now it is clear that at the expense of this W, you can destroy neutral ones. Okay? So, the torus is divided in 2 regions by some analytic curve. Into D plus and D minus. This is where orientation is preserved, and this is where orientation is reversed. This is called caustic. And now instead of considering
So it should be 0 on this line separating.
on separating line, Jacobian is 0.
Yeah, which means that it's critical.
This means that this is an analytic curve, critical line, which divides the whole into 2 things. And let me better consider phi here. Okay, and we are interested in zeros of this phi. So it's clear that you can choose arbitrarily small w so that no zeros lie in this. Yeah. Okay, so this proves the theorem in general, and now remains the most interesting part. So, for which tau or j we have 3, and for which tau or j we have 5. So let us count more carefully. So as I said in the beginning, there are 3 fixed points which always exist, and which are called trivial fixed points. I made a picture of the torus, and but now let me give a more rigorous argument why there exist 3 trivial fixed points and find them explicitly. So it's a very simple argument. So an even periodic function has half period the critical point. For an even periodic function, A Well, if the period is omega, then f of minus omega 2 equals f of omega 2. Yeah. On the other hand, f prime is odd. It has the same period, so we conclude that f prime. So this is a formal proof of existence of those three evident trivial critical points. Okay. So the three trivial critical points are just half periods. Okay, critical points of green function, and for our function, they are fixed points. Okay. Okay. And now let's consider cases. So first, case A, all three are repellent. They are fixed points of G. Then by our count, so n plus is attracting and minus is repellent, so there must be two attracting. Right. And they attract the two critical points. Case B, one of those is attracting. But our function is odd. So it is also odd about half period. And the critical points are C and minus C. So that one must attract both. Okay. So we have a dichotomy. And where is the boundary? When one of the trivial points is neutral. So the boundary curve okay, and this is can of course be easily computed because we know all of them and we know the derivative. And now I will tell you when this happens. Okay, so this happens if and only if this happens if and only if the imaginary part of eta plus omega E over one of the imaginary part of one of these three ratios is zero. Okay. So these are three funny modular forms. And now I want to show you something. So this is what does the separation in the parameter space. So now let me, okay. Doesn't work.
It's okay. Huh? It's like the light screens when the students does work. I'm telling you
It will start? Okay.
Yeah.
Ah. Okay, so oops, why don't we see anything?
No, 1 minute, please.
Okay.
Eat up or something. Yes, we can almost see.
Okay, maybe the light should be.
Wait.
Oh. No. Weierstrass.
Yes.
Yes, we'll drop one.
Is it better now?
Yes.
Yes.
Okay.
It's better in a second.
So the gray is the region where we have 5 solutions, and accordingly we have one metric of constant curvature 1 with such singularity on the torus. So these are the green regions. This is tau plane. Okay, so this is the green region, and the solid lines are boundaries of the fundamental region of the modular group, usual modular group, which maps tau plane to J plane. Okay. Now I can show you the picture in the J plane. That is the image of this region. No, it is not this. It is much simpler. Here it is. So this is the picture in the J plane. Okay. So 0 corresponds to hexagonal torus, and 1 corresponds to square torus. So in particular, on the square torus, we don't have such matrix of constant positive curvature. On hexagonal, we have 1. So here we have 1, and here we have none. Okay? Now, there is a very interesting point here. So what kind of torus is this? So I want to temporarily use the blackboard, but then I will want to use the screen again. So is it visible now here? Okay. So we found that this is a very famous torus. Here. Okay. Well, of course, the most famous are hexagonal and square because they have automorphisms. But this is what we found is probably the second most famous. So it was first encountered by Euler in 1744, which is about a decade before Euler got interested in elliptic integrals, which starts the whole business. And he encountered it in the following problem. So imagine a steel ruler made of steel. Okay, so it's flexible. So the shape of this steel ruler is called elastica curve. Okay, so Euler, following Bernoulli, was investigating possible shapes of elastica curve. So variational calculus was developed for this. And he found that all elastica curves but one are periodic. And one of them is compact periodic and has the following shape. And it is parameter, so this is called Euler's elastica. And he parameterized all elastica with abelian integrals. But this, so there are, I'm sure, sorry, there is also trivial elastica, which is also compact, so it's a circle and such figure eight shape. And this corresponds to abelian integrals on a torus. Well, with this shape. Well, it can be characterized in many various ways, but this J seems to be a transcendental number, though I don't know any proof of this. Okay, now next was alpha. Alpha investigated the second derivative of theta constant. And it corresponds to exactly the same terms. I don't want to define what is theta constant, but it is a simple equation like this. So this equation has a unique solution on 0, 1. And it is e to the 2 pi I tau, where tau corresponds to this torus. Okay? But this is not the end of the story. This is not the end of the story. So then, Gonchar and Rachmanov in 1987 they were solving approximation theory, the problem of approximation theory. They were studying the best rational approximation uniform. Best uniform approximation of E minus X on 0 infinity by rational functions. Okay, so if the error of approximation is En, then it turns out that En is asymptotically like geometric progression. K is the same constant. This equation. Okay, So they were also puzzled and found another characterization of this constant. So consider the function equation ANXN equals 1/8. But AN is the following. It's a sum of divisors of n with signs. Okay? So you take all divisors of n, put them with signs, and add and take absolute value, and this is an, and then use this an and solve this equation, and it is the same constant. Okay? And finally, Viper and I, we found that all these constants are related to this point, and then I found one more description of the same constant. It is the modulus of the following quadrilateral. This is a quadrilateral with angles 3/2, 3/2, 1/2, 1/2. Okay, so the feature is that these are aligned. It's a unique number, it's a modulus of scaling invariant. Okay, it doesn't depend on it, it's the same number. Okay. So this is a famous torus somehow. But I don't know whether J to this torus is algebraic or not. Because if it is algebraic, then it immediately opens the floodgate of connections with number. Probably not, but I don't know. And now, what I also wanted to show you is the Julia set. So returning to the dynamical system questions. So this is a very, I would say, ordinary mainstream holomorphic dynamical system. When you look at the Julia sets, you see what you expect. Here they are. Okay. So these are two pictures of Julia set corresponding to square and hexagonal torus. They are in different components, in different hyperbolic regions. Well, Julia says like Julia says, yeah? And I can zoom it. Okay, and next is the Julia set corresponding to dividing curve. Here it is. So this has a neutral basin with two petals. As it should be, there are two critical points conversion to it. And this happens for that very famous constant, which I just described. When parameter is equal to this very famous constant. So this is not actually the case. This is something else. Okay. And now, from the point of view of, I have not told you everything I wanted. So, from the point of view of metrics of positive curvature, well, this is only a very, very special case, namely the smallest odd angle of the singularity. And this is a major drawback of this method, that it works only for very, very special problems. Okay, one cannot generalize it. So the general question, I can tell you some history. So let us consider such algebraic equation. Yeah, and these are two polynomials of degree m and n. Okay, so the question is, how many solutions can this have? Well, first of all, this can have infinitely many solutions. But to exclude this case, I assume that m and n are not equal. Then we have finitely many solutions. Now, how many? Well, you can write everything in terms of x and y, and obtain two real equations, two real polynomial equations in x and y of degree bigger of this m bigger than n. Then you will obtain a system of two equations of degree m, so it has m squared solutions by deductive. Okay. And this is best possible. But if n is much smaller than m, expected is linear in the bigger one. Something like this. The number of solutions. Linear in the bigger power. And this is known only when n is 1. That is exactly for the type of equation which I'm considering here. That is when z equals f of z bar. Okay? So if f is rational, of degree d, then it was shown by Avinson and Newman that the number of solutions is at most 5 minus 5. And this is best possible. And it is in the previous work of Avinson with Schwiontek. They proved a similar result for polynomials. So the method of the proof combining Fatou theorem with degree belongs to and was first used in this paper of Avinson and Schwiontek. It's interesting that this is not only best possible, but this solves a famous problem from astronomy, which is related to gravitational lensing. When light from a very remote object reaches us and passes in its way through some regions occupied by mass, it's curved by this mass. And it may happen that we see, instead of one source, we have see it multiply. multiple stars where there should be really one star. So these are multiple images of one star. And the question is, how many images can we see? And assuming that this curving of the light is made by finitely many point masses, this gives the estimate of the number of images. And astronomers were working on this for a long time, since Einstein, who discovered the phenomenon. And they did find examples with equality and conjectured this inequality, which was proved by Harrison and Newman. But unfortunately, it's actually not very new results in some years past. No one knows what to do if n is not. What if n equals 2? One would be tempted to consider dynamics of some algebraic function, but you cannot really iterate an algebraic function. You cannot really even state for two figure for algebraic function. What could it mean? So, from the point of view of metrics, so here is the smallest next control problem will be, so this was with angle 6 pi, so the next problem will be with angle 10 pi. And it is equivalent to the following system of equations. So the first equation looks very similar to the one that I considered. Okay, so A times this plus B times conjugate zeta of A2 and zeta of A1, where A and B are the same constants, very same constants. Unique constants which made this periodic. And since there are two variables now, there is an additional equation. That is it. Problem, how many solutions can this have? Modulo periods. And the conjecture is 2 at most. And there is a picture illustrating what happens, what should happen. Here it is. This is a picture in the J plane. So this is conjectured shaded area is conjectured projection of the moduli space of matrix, what I call SPH, to the moduli space of tori, J. Okay? So we found the boundary of this projection rigorously. So for this curve, we know the equation. But we don't know that the mapping is open. So we don't know that the image of our region is bounded by this curve. Okay, so this is the relative boundary, but it can have faults a priori, or some pieces which project here, which we just don't see. And this is not known. And this is such a simple system. Of course, it can be solved numerically. Numerical computation confirms this result. Okay, so I'm finished.
Are there any questions?
Well, I wanted to ask, but this is not mathematics, it's physics. So what would be D in for the gravitational lensing?
What would be
Because
what?
the estimate of
In gravitational lensing, the number of point masses which do this distortion, this gravitational distortion.
okay, so if there's one,
Huh?
so if there's a 1 point mass, the bound is by
No, this doesn't work when d equals 1, sorry.
okay.
When d equals 1, I saw the degrees must be distinct. When d is 1, you can have infinitely many images.
Then you can have,
This is called Einstein ring.
yeah,
Yes,
yeah,
yes.
yeah.
So by one mass, you can have a circle, actually. And this is called Einstein ring, and it was observed, and so on. But for 2, 3, and more, this
That makes sense.
You also said that your method is sort of not generalizable for a bigger alpha, right? So,
no.
but
Well, this is what we have for next alpha.
and what about the tools that people are using in the original papers? Is it like you said?
No, they cannot. They are working hard on this, and they cannot go to next alpha. So it's a major unsolved problem in the area. Simplest case of it.
And one short question: what exactly is this funny quadrilateral is used for? Is that you said the modulus of this?
Well, funny quadrilateral.
Okay.
What else can I say? Its modulus is related to all those modulus. Okay, so there is some special torus which arises everywhere. Well, in all these contexts which I mentioned, which is neither square nor hexagonal, that's all I can say. We know hundreds of digits of tau and J for link, but I don't know whether J is rational.
But I have one more question. So this happens for the angle 10 pi. What happens for the angle 14 pi? Is it still like?
I can show you the picture for 14 pi. So
Actually, I don't have the picture. I want the equation. So what's the third equation? Because then you need the third.
I can.
Is it very complicated or is it?
No, it's not very complicated. Let me see whether I have it. Well, I don't have it with me, but I can show it on the screen.
Okay.
I can show on the screen. The second, the general system of equations, yes. So all of them but one are analytic, complex analytic. Only one, which always looks like this, I will show you, is not complex analytic. And the rest look very innocent, actually. Here they are. Zoom. Here they are. So you see, the first is not analytic, and it is of the same form. So you have sum of zetas and linear and antilinear form. Yeah, and same AB. AB are the same. Okay, and you have n equations like this, analytic. Here there is one analytic, and in the case I consider there is none. Only anti-analytic.
We understand these kids before.